Welcome back to the Explainer. So now that we've got our mental catalog of basic everyday functions dialed in, it's time we learn how to really manipulate them. We're moving from just looking at math to, actually building with it. Today is all about a huge idea in calculus, taking those simple textbook formulas and transforming them into complex, adaptable models. We're going to learn exactly how to build new functions out of the old ones.
Which brings us to a pretty massive question. How do we actually make these basic mathematical models fit complex, real-world data? Because, let's face it, the real world is totally messy and unpredictable. A perfectly smooth, standard parabola rarely maps perfectly to a rocket fighting wind resistance, right? And a basic exponential curve doesn't just magically fit a city's population growth without some serious tweaking for things like limited resources. We have to move past those rigid formulas. We need a real builder's toolkit to shift, stretch, and combine these functions so they actually match what we see in the real world. Okay, let's dive into this. Part 1, building with blocks. Think of our basic functions as basically raw building materials. In calculus and really in any advanced modeling, we almost never work with raw, naked functions straight out of the catalog. They're just the starting point. The real magic happens when we mold them to our exact needs. Take a look at this naked function on the left. Y equals x squared. Just a simple, beautiful parabola sitting right at the origin. But watch what happens when we morph it into this dressed-up version on the right. Y equals 2 times the quantity x minus 3 squared plus 1. It's the exact same fundamental shape, but we've completely manipulated it to fit a new reality. That minus 3, it shifted the whole thing horizontally. The 2 stretched it vertically, making it way steeper. And the plus 1 just lifted the entire curve right off the x-axis. By using these specific tweaks, we take a generic block and custom fit it to a precise spot. This is exactly how we start modeling reality.
Moving right along to section 2, shifting and reflecting.
So to do this efficiently, we really need to master the hand tools of our mathematical workshop. These are your everyday operations that let us move, stretch, and flip graphs around without having to agonizingly calculate every single point. Let's walk through the formal rules for these tools. First up, vertical shifts. If you have a constant c and you add it completely outside the function, like f of x plus c, you just slide the whole graph up. Subtracting c outside the function slides it straight down. Makes total sense, right? You're just directly changing that final y value. But horizontal movements, they're a bit different. If we mess with the input directly inside the parentheses, the whole graph shifts left or right. We're changing the x value before the function even gets its hands on it. And finally, reflections. Slapping a minus sign entirely in front of the function, so negative f of x, acts like a mirror. It takes every positive y value, makes it negative, and vice versa. It literally reflects the whole graph over the x-axis, flipping it completely upside down in one shot. Now hold up, pay super close attention to this next part because it is a huge trap. Watch out. When you subtract c inside the parentheses, like f of x minus c, it actually moves the graph to the right. No way, right? I know, your intuition is screaming that a minus sign should pull you left towards the negative numbers. But think about the logic for a second. To get the exact same output you used to get at an x value of 0, your new x input has to be larger to make up for that subtraction you just forced on it. You literally have to feed the function a bigger number just to break even. Because of that, every single point on the graph gets pulled to the right. Memorize this counterintuitive rule for sure, because understanding the why will save you so much grief later. All right, section 3, the function chain. Now that we've got a handle on the hand tools, let's bring in the heavy machinery. The absolute most powerful way we combine functions is called function composition. And let me be super clear about this. Composition is not just simple multiplication. It's an assembly line. Now, what's really interesting about this slide is how it perfectly maps that out. In a composite function, which we write as f of g of x, we start with an input x. Step 1, that x goes into machine g. Machine g does its thing. Step 2, out comes the result, g of x. Now, instead of stopping there, step 3 kicks in. That entire output becomes the raw input that gets shoved straight into the next machine, f. The final result is f of g of x. We run the inner function g first, and then the outer function f processes whatever g spit out. It's a chained sequential flow. So the crucial point here is the strict quality control on this assembly line. We have an absolute, non-negotiable rule about the mathematical domain. For f of g of x to even exist, the output from that first machine, g, must be a valid input for the second machine, f. Think about it. If machine g spits out a negative number, but machine f is a square root function, which, can only handle positive numbers, the whole chain just completely breaks down. The gears jam up and you get an error. The domain of our new composite function is totally restricted by what both machines can handle in sequence. Always check if the handoff is mathematically legal.
Which leads us to section 4, why order matters.
Since this is a sequence, you might be wondering, does it really matter which machine goes first? Like, what if we run it in reverse? Let's look at a counterexample, and this brilliantly illustrates why order is literally everything here. Take the sequence on the left. We subtract 3 first, then square the result. That's x minus 3, in parentheses, squared. Based on the rules we just went over, tweaking the inside of the parentheses gives us a horizontal shift to the right. But look at the right side. If we swap the order, square the input first, then subtract 3 at the very end, we get x squared minus 3. That subtraction is outside the squaring function, so it creates a vertical shift downward. Just by swapping the order of the machines, you end up with 2 completely different graphs in completely different locations.
So, to sum this all up real quick, first, the composition f of g of x is almost never equal to g of f of x. They are completely different operations. Second, as we just saw, the order completely changes the physical transformation. A horizontal shift can turn into a vertical shift just like that if you mix them up. The main takeaway for you? Keep your assembly lines straight. Always know exactly which function is on the inside acting first and which is on the outside acting second.
And finally, section 5, the final challenge. We've covered some really crucial ground today, going from those basic naked functions to some highly customized mathematical models. So let's put your new toolkit to the test. If your base function is f of x equals the square root of x, what is the exact algebraic formula for a graph that is shifted 2 units to the left and 4 units down? I want you to write your formula down in the comments. Let's see how well you've nailed these transformations. And definitely get ready, because in our next explainer, we're diving into the actual beating heart of calculus. We're tackling limits. See you there.